Bonjour tout le monde, merci beaucoup. And thank you to all the other presenters for giving a really good background to my talk, albeit perhaps a little bit redundant, but hopefully have something insightful and new to share. So thank you very much for the introduction. My name is Michele Faragalli. I'm the CTO of Mission Control. So Mission Control builds software for the Earth, Moon, and Mars. Our focus is on modernizing software for creating more intelligent insights into space mission operations, as well as enhancing the autonomy of these missions. Our activities are focused around two main product lines. The first being Spacefarer, which is a web-based operation platforms for robotic operations. It's been used in thousands of hours of analog mission operations by us and by our customers in various places around the world, and hopefully very soon you'll be seeing it operating robots on the surface of the moon. Our Spacefarer AI is a suite of tools and technologies and methodologies that we've developed to deploy artificial intelligence onto space flight computers. And that's enabled us to actually gain some really interesting firsts in space, including the first neural network to fly to the moon. We're the first organization to do that. We did that earlier this year. One of a handful of organizations who've flown neural networks on an FPGA in low Earth orbit. And to our knowledge, we believe we are the only Canadian organization to date to fly deep learning actually in space. Well, I guess it's going forward. So why do we need AI on board to begin with? So my focus really is on deploying these algorithms on board the space computer. We're already seeing AI having an impact throughout the entire value chain of space. We talked a lot about upstream and downstream applications, so I won't kind of go over them too much. But suffice it to say, in operations, decision support for ground-based operators or data services on, processing Earth observation imagery is a really common application. But most of those applications still operate on the ground, so on the ground segment of these space missions, and they tend to not really focus on deploying them on board. The need to deploy them on board is really driven by time constraints or latency requirements of those missions. So two really good examples in operation is, of course, the further you go out in space, the longer the latency is, and having a human in the loop to make decisions, view the data, and then send commands is just, it's going to limit the paradigm under which you could operate space missions, of course. On the data insights side, what you'll see oftentimes in most Earth observation applications is you could do that on the ground, but not in the case where it's a time-sensitive response. So let's say emergency scenarios, disaster scenarios, or even more complex operations where one satellite needs to task another satellite to image the Earth in an emergency scenario. That's the kind of thing you want to push on board, because then you can gain efficiencies through that kind of operation. The notion of onboard autonomy, though, isn't necessarily new. Some of the presenters talked about that today. I think Curiosity, Perseverance are good examples where there is autonomy on board these missions, whether it's path planning or instrument targeting, that exists, but they use more shallow learning methods, so classical techniques, machine learning techniques, and you're not seeing a widespread adoption of deep learning techniques on these classes of missions. And deep learning, just to remind everyone in the audience, has really been the state of the art in solving problems for the last decade or so in computer vision, natural language processing, or any kind of generalized AI type problem. But we're not seeing that really widespread in space. Why is that? Well, space is a little bit different than our terrestrial sectors. I kind of like to think of it as a bit of an iceberg. So we tend to focus on the deep learning model, training it and solving object detection problem as an example. That's a really important part of the problem, but it kind of ignores some of the unique features of space that are, I would call, beneath the surface. So first of all, we talked a little bit already about the lack of training data in a real operating environment. We unfortunately can't just go outside and fly around and get that data. We have to launch a rocket, which is very expensive, and go get that data before we could even have suitable data to train on. So that's a bit of a catch-22. Frankly, we're talking about flight software, and there are standards around verifying and validating flight software, but none of them have really been designed around these types of data-driven algorithms. So how do you handle that? There are significant computer limitations of these spacecraft. I think the last presenter mentioned that. We have spacecraft that have 20-year-old compute abilities, so that's a problem when we're adopting more modern algorithms that are used on the ground. So there's a gap there, a technology gap. And generally speaking, just to do all of this, there's a lack of standardization and tools that exist in the market. So what do we do at Mission Control? Well, we think it's really important to know when and how to use deep learning to solve your problems. Number one, you have to select suitable problems to solve. There needs to be data. The deep learning approach needs to be well suited to solve that kind of data. And the operational context has to be considered from day one. You don't just want to be developing algorithms for the sake of it. Number two, you want to consider the entire robustness of your, sorry, I'm getting a phone call. I'm sure it's not important. So you want to consider that whole pipeline of reliability in quality control and quality assurance throughout the development cycle. We saw that this morning in the aerospace talks about how do you manage requirements throughout the development of these development cycles, which tend to be highly iterative in nature, which is sort of incongruent with how a waterfall design process typically that you see in a space mission. And then ultimately, in space, we tend to think of, you do all your rigorous testing on the ground, strap it to a rocket, fly it in space, and hope for the best. Paraphrasing, but generally speaking, that's the philosophy in space. The reality is with these data-driven techniques, it's going to have to evolve. So you're going to have to fly something that might not be ready to be used yet, but over time, you may want to think about commissioning it. So you want to monitor that performance and potentially upgrade it over time. The same way we use machine learning on Earth, there are software patches, there's software updates. That might be an interesting approach to adopt for space. So what are we doing at Mission Control about this? Well, we do very much focus on solving problems that we identify in our domain of expertise, but also working with partners who may see a benefit in working with us to solve their problem using autonomy on board. We either use publicly available or custom data sets by our customers or generate them ourselves. So we have an orbital robotics lab. So you see the GIF in the top right-hand corner of a client spacecraft that you might want to approach and service in space. That's in our lab. We use that to generate data sets. We have a moon yard facility, an analog moon environment that's indoors to create high visual fidelity images for our computer vision algorithms. And then there's a whole portfolio here. It's just a snapshot of what we've done so far that I can show, but generally in the realm of robotics, guidance, navigation control, autonomous science, instrument targeting, but also even looking at downlink prioritization. So you might be intelligently compressing images so that you can save bandwidth, or even triaging your images before you send them to the ground so that either you're sending your more high-value data down quicker for your operators, or you're just highlighting, you're not wasting kind of that bandwidth on images that are kind of useless for your operations on the ground. I alluded to this earlier, but we've kind of developed this whole pipeline of how you would actually go through your design and development process to take a deep learning model and fly it on board a spacecraft. So that really starts with user needs, then generating data, generating your models, which is a highly iterative cycle. And so quality assurance and quality control is a really important part of that for reliability and trustworthiness. Then what we've done also is we've kind of developed a unique piece that goes from your high-level machine learning model and deploying it to your kind of compute-constrained environment or your flight computer. And that we developed our own compiler in order to take that high-level model and deploy it to really any kind of compute architecture relevant for space, CPUs, and FPGAs in particular. And what else are we doing while we're flying? Because a big part of this is actually gaining that heritage and that experience. So I'm going to talk briefly about 2 flight demonstrations that actually occurred this year that we're quite excited to share about. The first one is our MoonNet algorithm, which is a semantic segmentation algorithm that does terrain classification. That was deployed on board iSpace's lunar lander. About a year ago, it was launched. It was processing images from a rover that was being ingested. And we successfully tested and validated that entire pipeline and flew that algorithm on board a CPU that flew to the moon, which is the first time that was ever done. We confirmed the functionality in deep space. Unfortunately, as many of you may have heard, that lander did not soft land on the surface of the moon. So unfortunately, we did not complete the onboard inference on the surface of the moon, but we did have the entire infrastructure to update that model in flight. So we were anticipating a performance boost mid-flight, which was part of our kind of approach and philosophy to that. And by the way, AIT was done in Germany. Just 2 more slides. So the second experiment we did earlier this year was on board ESA's OPSAT, and we hybridized the SmartCam classifier onto an FPGA, becoming, I think, the second or third organization in the world to ever deploy a deep learning model onto a spacecraft on an FPGA. So these are some images from our successful demonstration earlier this fall. And we kind of use that same pipeline, that same methodology to a different hardware target with a different model. And the performance matched exactly what we expected, which was great. Last slide. So deep learning at the edge in space, it has a lot of potential, which I talked about, so I'll jump over that. But there's still barriers to adoption. A lot of it has to do with the philosophy behind how and when to use these approaches, which can circumvent some of the limitations that I've talked about and some of the other presenters. We're always interested in talking about partnerships, but what I really want to end on is this cool picture. So OPSAT happens to be a tumbling satellite, takes pictures of Earth and space, and so there's obviously a non-zero probability that it will take a picture of something interesting in space. And during one of our experiments, it took a picture of the moon. So what was really cool about this picture is that our second AI experiment took a picture of our first, which is really cool. Thank you very much.
Thank you.